Non.
Yeah.
Okay.
And mic on. Mic on. I think it should be okay, right?
Yeah.
I think we'll start recording it.
What do you mean main picture?
It's just that.
Ah, okay. Okay.
Isn't it that main picture?
I think that should be okay.
Okay. Fine.
It's not.
Not a huge problem. But actually, I will send you again the slides. They are pretty much the same as the last time.
So, yeah, I guess we'll just start, right?
Yeah, sure. Yeah, so good morning, everyone. So my name is Pascal Nob. I'm at Imperial College since about 3 months ago. I arrived 3 months ago, and I will leave at the end of July. So this morning I'm going to talk about modulation of periodic wave train, but let's say from a formal point of view and spectral point of view. And the next two lectures on Friday will be dedicated to, let's say, more analytical stuff, and how do you prove nonlinear stability, or you deduce nonlinear stability from spectral stability. Okay. So this is all these works are joint work with Luis Miguel Rodriguez from University of Rennes, Kevin Zombrun from Indiana University, and Matt Johnson from Kansas University. And okay, so let me start with some motivation. So various words of introduction. So periodic waves usually comes as hydrodynamic instabilities. And where do you find hydrodynamic instabilities? In nature, of course, and in experiments as well. And I show you the first two examples of hydrodynamic instabilities. The first one concerns rolls in Taylor-Couette flow. So maybe you know already this experiment, but what is a Taylor-Couette flow? So you actually you put a fluid between two rotating cylinders, one rotating like this and the other like this, for example, or you can consider also that they rotate in the same sense, but at different speed. Okay, So you strain the fluid inside between the two cylinders, and if the Reynolds number is large enough, what you get is that you get the operation. What comes up are what is called Taylor vortices. Okay, so you have various pictures. So at the beginning they are straight, and if you increase more the velocity, they start to destabilize, and you get more and more complex situation. Okay, so this is the very first example. The second example comes from Rayleigh Benard convection. Actually, you already see this when you heat up some fluid in your pan. You see some patterns. So this is an example of patterns. So what is a Rayleigh Benard convection problem? You put a fluid between two flat planes, okay? And you start to heat it up from below, and convection starts, and you get some patterns. Okay, so usually what you see from above are 2D patterns, okay, but in 1D it looks like this. And if you increase the gradient of temperature, you get more and more complex patterns. Okay, these are two examples of hydrodynamic instabilities. Other hydrodynamic instabilities, and basically this is the way I came into these topics. These are free surface instability. They are called roll wave, and they usually appear in gravity-driven flows. So imagine you have a flow of water flowing down an incline. So the incline can be vertical, okay? And maybe if you the day you have heavy rains, you see some patterns on the glasses of a building. And here, but this is very chaotic, and here this is the very beginning of the hydrodynamic instability. As you may see, okay, it's not exactly periodic, but it's quite periodic, okay? And I will come back to this notion after that, okay? So, and here you have sort of 2D hydrodynamic instabilities. It's in 2D, and you see already that it is the very beginning is, let's say, quite flat, and then you have 2D patterns like this.
So the difference between left and right is that it's narrower, is it?
Yeah. Yeah, and I think actually the Reynolds number is larger here. So, or equivalently, the discharge rate is more important at this place. Okay, but you see all this kind of pattern in nature. Okay, and here, where does the instability come from? So actually, you have two phenomena in this problem. So you have gravity versus bottom friction. Okay, so in this case, gravity destabilizes the flow, and friction stabilizes. So it's a competition between those two effects. And if this, let's say, is bigger than this one, okay, you get instability, and you get the fact that you get free surface instabilities. Okay, so another motivation of studying periodic waves is more or less to study more complex patterns in nature and to use them as building blocks. Okay, so you have various nonlinear waves that are of interest. So you have solitary waves. So it's just a self-similar solution propagating at some wave speed c, and the end state here and here are the same. Okay, so these are solitary waves. So you have shocks. So shocks is a self-similar solution propagating at some speed, so c, but it connects two different states. So you can talk about shocks, about kinks, stuff like that. And the last, let's say, typical solitary waves are periodic waves. And you can combine all these nonlinear waves to build up some more complex nonlinear waves. So you have one famous example. These are called tidal bore. So it's a bore. So you all know what a bore is. So what is a bore? So you have, let's say, tidal that come from, let's say, ocean. Okay, and this enter into a river. And what you get when you have this, you get a sort of a front, okay, or a shock. But the fact that you have no breaking, okay, usually what you see on a beach is breaking, but in this situation you don't see breaking because you have very important dispersive effect. And what you get is a shock that is regularized by dispersive effect. So usually when you see a shock, you see that this particle go faster than this one, okay? So this should induces a breaking, but because of dispersion, what you get is that it starts to oscillate, and the oscillation grows with time, okay? And you get what is called, let's say, a dispersive shock. It is called a dispersive shock. Maybe a better way to talk about this shock is to say it's a shock regularized by dispersion. Okay? So I will come back to this terminology later, but what you see is that, so this is a typical example of solution of KdV equation. So the KdV equation reads like this: ut plus ux plus epsilon ux xx equals 0. Okay? So if you get rid of dispersion, okay, and you start with a step, okay, in finite time you get breaking, and you propagate with some constant speed, okay? But because of dispersion, this picture is replaced by this one, okay? And why do we see this pattern? So let me, and not a shock. So actually, if you consider another equation, ut plus ux equals epsilon, or let's say delta, uxx. So this is viscous Burger's equation. Okay? And actually for viscous Burger equation, if you want to connect two constant states, okay, with a traveling wave, it's possible. Okay? So we can connect two different states with a traveling wave. Okay, so if I'm looking for a traveling wave of this guy, so it's minus cux plus u square over 2x called delta uxx. I can integrate let's say between minus infinity and x, what I get is minus c u minus u minus plus u square over 2 minus u minus square divided by 2 equal delta ux. Okay, so this is a first order differential equation. You can draw the fast portrait, and actually you can see that you can connect two different states, u minus to u plus, and u plus is just so connection u plus u minus, and u plus satisfies this relation. Okay, and this is nothing but the Rankine-Hugoniot jump condition. Okay, if you try to do the same job with KdV, so the solution that is here, what comes up? So let's try to connect two different states with KdV. So KdV, the equation of profile reads like this. Yes?
Suggest you switch it around.
Ah, okay.
The recording is not, the screen is not showing.
Okay, and
On the left, I think the left, no?
yeah. So for KdV, the equation of profile is this one. So you can integrate one time. And you get more or less an equation of profile like this. Okay, so you substitute the first derivative by a second order derivative. And okay, if you go a little bit deeper in details, what you get, so maybe the sense of my first portrait will not be correct. So basically you get u minus and u plus. So you have another solution. But actually what you get is that one of these 2 points is a saddle point. The other one is a center. Okay, it's not a saddle point anymore. And what you get is this fast portrait. Okay? So there are no traveling wave that can connect u minus to u plus. Okay? So if you want to connect two different states with a KdV equation, what you have to do is to travel, let's say in some sense, travel across the so what you get here, so it's a center. Those one are periodic waves. So this wave for KdV are well known. They are cnoidal wave. The wave that it's here, it's a solitary wave. Okay, well known also for KdV. And if you want to connect two different states with, let's say, some moving pattern, what you have to do is to travel across the family of periodic wave. Okay, and this is what you see on the picture. The leading edge is more or less the solitary wave, a portion of the solitary wave. And then, when you go back in this direction, you travel the full family of periodic waves. Okay? So, to do so, you have to modulate the parameter of the periodic wave to meet let's say, the trailing edge. Okay? So, this is another motivation to consider periodic waves. If you modulate those periodic waves, you could be able to develop this kind of solutions. Okay, so yeah, so now I will write down some equation to illustrate those type of instability. So actually, I split this instability in, let's say, two sets. The first sets are more or less the first hydrodynamic instability I shown you, sorry. So Rayleigh Benard and Rayleigh-Taylor. And more or less what's going on is that, so you have an instability that comes from a very particular wavelength, okay? And this is due to the fact that you have some, let's say, geometrical parameter in your flow. So in the Rayleigh-Taylor, you have the dimension of the cylinder, the radius, etc., etc. So in some sense, it will impose a sort of scale of the instabilities. Okay, and the other part concern hydrodynamic instability in free surface flow, and in this case, actually, there are no real selection. Okay, so the instability will come with a different process. So for Rayleigh Benard convection, you can write equation like this. So Navier-Stokes coupled with an equation on temperature. You can study the stability of the constant state. So the constant state is nothing but the velocity is 0, and you have a constant uniform uniformity of temperature. So you write down a dispersion relation, and what you get is that for some parameter called the Rayleigh number, so if it's bigger than this value, so actually how do you get this dispersion relation? So the geometry of the problem is like this. So you get x1 in this direction, x2 in this direction, 0 and pi. Okay, the equation are the linearized equation are homogeneous both in the x1 and x2 direction. So in x1 you perform a Fourier transform. Okay, so this is a Fourier parameter, and in x2 this is not Fourier transform, it's Fourier series. So you get a discrete set of frequency, and this is written here. Okay, so you perform this Fourier and Fourier transform, Fourier series application, and you consider Laplace transform in space for the linear problem, and you get this dispersion relation. In time, yeah. So as you see, so you can choose the very first instability occurs when this one is equal to 1. Okay, so this is written here. And actually, once you have this, you can try to perform an expansion of the dispersion relation about this particular number to see how the transition from stability to instability happens. And so this is the dispersion relation, and actually you try to mimic this dispersion relation as if it came up from, let's say, a partial differential equation with constant coefficient. Okay, so lambda is time derivative, and k is spatial derivative. Okay, and when you replace let's say lambda by derivative of time and k by some derivative in space, you end up with this equation. So the linear part of this equation mimic the dispersion relation that is written here. Okay? And if you want to build up some nonlinear evolution equation for this problem, you add the nonlinearity. And the nonlinearity is written here, and you end up with what is called the Swift-Steinberg equation. But as far as I know, there are no proper derivation of the full Swift-Steinberg equation with the nonlinear term. Okay, you can derive properly the linear part, but the non-linear part, if you start from Rayleigh Benard equation, you get a very difficult nonlinearity to express, and so you substitute this nonlinearity by some heuristic nonlinearity. Okay? So the Swift-Hohenberg equation is a sort of, let's say, a heuristical equation. Okay? From this equation, if you perform a small amplitude and small wave number limit, so you assume that the perturbation of a small wave number what you end up with is what is called the Ginzburg-Landau equation. Okay, and this one you can derive it for real, either for Swift-Hohenberg equation or directly from the Rayleigh Benard problem. Okay, so this is more or less an amplitude equation. So what you see is that it's a reaction diffusion equation. That's it. Okay, except that the amplitude here can be complex. Okay, so you find out this kind of Ginzburg-Landau equation in many situations, and you can do the same play the same game for other situations like Rayleigh-Taylor. Okay, so now I go to the other type of instability. These are free surface flow. So now the problem is Navier-Stokes equation down an incline with a free surface. So how do you formulate the problem? So basically you assume that the incline is infinite. Okay, it's not very physical, but anyway. So you consider an infinite plane and a flow that is flowing down. You have an inclination here, theta. Okay, and you can model, so here you have Navier-Stokes equations. Okay, and you have a free surface. Okay, so let's say the free surface is parameterized by, let's say, the fluid height. Okay, so you have Navier-Stokes equation plus many boundary conditions. Actually, this problem is very hard to tackle because, okay, Navier-Stokes equation is already a very hard problem to deal with, but now the surface is moving and is depending on the solution. Okay, so it is very hard to let's say, describe a nonlinear wave in this situation. So what usually people do is to try to derive a set of simplified equations, and these are called the shallow water equation. So shallow water equation is just averaging Navier-Stokes equation